Welcome to Homework Lib.
We want to calculate the percent of ionization of formic acid, which is going to have the following reaction in the presence of water to generate the acetate ion plus H2O plus. All of this is going to be in aqueous solution, liquid, aqueous solution, and in aqueous solution. The information that is given to us is that the value for Ka is going to be equal to 1.8 times 10 to the minus 4, and that the initial concentration would be 4.70 times 10 to the minus 2 molar concentration. So in order to solve this, we're going to start with writing down our ice table. This ice table is going to have initial concentration. The water is not going to enter into our equilibrium equations, 0 and 0. A fraction is going to react that we're going to call minus x, plus x, and plus x is the quantities that are the quantities that are going to be generated. So at equilibrium, we're going to get C0 minus x, x, and x. So according to our equation for Ka, this is going to be equal to the concentration of the conjugate base, HCO2 minus, times the concentration of H2O plus, divided by the concentration of the formic acid, which, replacing the values at equilibrium, corresponds to x squared divided by C0 minus x. So over here we have two options. Both of them are going to give us very similar results. So the first one is to solve the full quadratic expression that comes from this. So the quadratic corresponding to this equation would be equal to Ka times initial concentration minus Ka times x is going to be equal to x squared. Thus, the solution would come from x squared plus Kax minus Ka multiplied by C0 equal to 0. So replacing the values for my initial concentration and the acidity constant, we're going to find that the value for x is going to be, of course, this is a quadratic expression, so we're going to have two answers. One is minus 0.003, which is going to have no physical meaning, and the other one would be 0.00282. Remember that these quantities can come from solving the equation either on your calculator or employing the general formula, which tells us that x plus minus, or 1, 2, would be equal to minus b plus minus the square root of b squared minus 4 times ac divided by 2a. And in this case, the values for a would be equal to 1, the value for b would be equal to Ka, and the value for c would be equal to minus Ka times C0. Okay? So the result that we're going to take as valid is going to be x2 over here. This is the result without doing any approximation. So x2 is going to be equal to the fraction that dissociated. So this is going to be equal to the concentration of HCO2 minus that we're going to have, and is also going to be equal to the concentration of H2O plus. So this would correspond to 0.00282 molar. Thus, the percent of ionization is going to be equal to the fraction that was ionized, so 0.00282, divided by the initial quantity, 4.70 times 10 to the minus 2, and this multiplied by 100. So gives us a 6% of ionization. So this would be the correct answer. Now, for sake of completion, let's look at what would happen if we employed the small x approximation. Under this approximation, the value for C0 minus x is going to be approximately equal to C0. So with that, the value for Ka is equal to x squared divided by C0. Thus, x would be the square root of Ka times C0, which gives us a value of x of 2.908 times 10 to the minus 3 molar, and thus a percent of ionization equal to this value over my initial concentration, 6.2% of ionization. So as you can see on the small x approximation, we're going to get a result that is similar to the exact one, but we're going to start to have some important deviation of a 0.2%. And with that, it would be all. Thank you very much and have a good one.